Welcome to The Explainer. Today, we're going to demystify the absolutely wild, hyper-complex engineering behind the new 2026 Formula One cars. So let's just dive right in. We're going to dissect the unbelievable physics and the sheer engineering of these modern marvels from the inside out. We really want to see exactly how these vehicles push the absolute boundaries of material science, aerodynamics, and hybrid power to hit speeds and g-forces that honestly barely seem possible. It is completely changing how Sunday races are going to be fought. Okay, here's what we're looking at today. First, the carbon fiber cocoon, then harnessing the wind, the 2026 hybrid revolution, breaking from 340 to 0, and finally, the ultimate data machine. Section 1. The carbon fiber cocoon and engineering survival. Our very first stop is right at the center with the driver. The driver is encased in this carbon fiber monocoque that acts as the car's primary load-bearing structure. It's basically an indestructible backbone. To make sure they survive catastrophic collisions, this cocoon features a survival cell lined with Kevlar, which is designed specifically to stop foreign track debris from penetrating the cockpit. Up front, you've got progressive crumple composite cones to decelerate the car in a really controlled way. Then, right above the driver, sits the halo. That's a grade 5 titanium hoop protecting the head from heavy impacts. And right behind them, a roll hoop rigorously tested to withstand severe 20G impacts. Crazy, right? Now, it's pretty crucial that this robust cell protects the driver from those massive forces. But you might be wondering, if you can survive hitting a wall at extreme speeds, how does the car actually stick to the track well enough to corner at 5Gs in the first place? Well, to answer that, we have to look at how the car manipulates the wind. Section 2. Harnessing the wind and the 2026 Nimble Car Concept. Downforce is what literally sucks the car to the asphalt. But to truly grasp ground effect aerodynamics, you absolutely have to understand the Venturi effect. By shaping the underfloor of the car like a convergent-divergent duct, aerodynamicists force the oncoming airflow beneath the chassis into a super-restricted area. Based on fluid dynamics, this causes a localized velocity spike and a dramatic drop in static pressure. So the higher pressure ambient air on top pushes against this low pressure vacuum beneath the floor, literally vacuuming the car right to the ground. But what's truly fascinating is how the 2026 rules have totally flipped this dynamic on its head. Because the new Nimble Car regulations actually reduce underfloor downforce by up to 30%. Teams now have to rely on a fully integrated active aerodynamic system. The cars are constantly switching between two setups. First, you have Z mode, which is a high downforce, closed flap configuration for quartering stability. And then there's X mode, which flattens the wings out to shed just massive amounts of drag on the straightaways. So, with active aero in X mode shedding up to 55% of the car's drag, they're slipping through the air with way less resistance. But what exactly is powering those blistering straight-line speeds under this new regulatory era? That brings us to Section 3, the 2026 hybrid revolution and the 50-50 power split. Welcome to the 2026 hybrid revolution. The whole powertrain target is now a strict 50-50 split between thermal combustion and electrical energy deployment. And the stark contrast from the previous generation, it is just incredible. The internal combustion engine power actually drops, but the electrical side completely takes over. That highly complex MGUH exhaust generator, totally eliminated. To make up for it, the MGUK kinetic motor connected to the crankshaft has nearly tripled in power. We're talking a jump from 120 kilowatts to a massive 350 kilowatts. Plus, beautifully, the internal combustion engine is now running on 100% sustainable synthetic fuels. Now, because the battery has become the absolute main character of the powertrain, drivers really have to strategically recharge it using 4 distinct methods. First, we have your traditional KERS-style braking regeneration. Then there's part throttle harvesting, where the car captures excess engine torque going through corners. After that, we have lift and coast, which happens when the driver lifts off the pedal early, sacrificing their active aero to harvest kinetic energy. And finally, there's the controversial super clipping technique. This is where the car automatically redirects power to the battery while the driver is still flat out on the straights. It slightly reduces their top speed, but it keeps their active aero fully open. And this hybrid system is incredibly robust. It can now harvest up to 9 megajoules of energy per lap. To put that number into perspective, 9 megajoules is roughly the kinetic energy of a mid-size family car traveling at 150 kilometers per hour. That harvested energy is stored up and ready to be deployed in these massive 4 megajoule bursts, giving drivers around 11.5 seconds of full electric boost per lap to either defend their position or go on the attack. But this immense electrical power creates a really unique engineering challenge. Because the powerful MGUK acts as a virtual parachute when it's harvesting, it applies an immense electromagnetic resistance to the rear axle. This drastically changes how the car slows down. So, what actually happens when a driver hits the mechanical brakes at the end of a long straight?
Let's find out in Section 4, braking from 340 to 0, the friction forge.
Think about this. To decelerate from 340 kilometers per hour to 0 in mere seconds, generating over 5 Gs of force, Formula One cars have to rely on pure carbon brakes. The manufacturer Brembo actually starts with soft carbon fabric sheets. First, they stitch dozens of these layers together in a needling machine. Then they bake the preform in a furnace up to 2,700 degrees Fahrenheit. This process is called chemical vapor infiltration, and it deposits carbon atoms directly into the weave. Finally, they use ultrasonic drills to bore over 1,000 tiny cooling holes right into the dense disc.
That intense 4-month manufacturing process is absolutely required. And why is that? Because stopping an F1 car generates so much friction that these pure carbon discs reach an incandescent 1,000 degrees Celsius during heavy braking. They operate in a remarkably narrow thermal window too. If they're too cold, there's a severe loss of initial braking torque. But if they get too hot, the material literally begins to oxidize and structurally degrade. And at those extreme 1,000-degree temperatures, even a slight loss of cooling airflow, like, say, a single sandwich wrapper or a helmet tear-off blocking a brake duct, that can cause an explosive thermal runaway and just melt a caliper. So the crucial point here is, how on earth do teams monitor thousands of these critical variables in real time to prevent disaster?
Well, that brings us to Section 5. The ultimate data machine, the invisible infrastructure.
A modern F1 car is essentially a high-speed data acquisition center. It uses up to 300 sensors communicating over a deterministic CAN bus network, tracking everything, and I mean everything, from infrared tire surface temperatures to the driver's biometric heartbeat. Every single steering input, thermal fluctuation, and hybrid power deployment is tracked and transmitted wirelessly. But exactly how much data does a single car produce over the course of just one race weekend? The sheer volume is staggering. Over just one weekend, a single car streams over 1.5 terabytes of encrypted telemetry. This data flies back to the pit wall and all the way to the factory mission control rooms via a proprietary WiMAX mesh network. And incredibly, they do all of this with barely 15 milliseconds of latency. This allows the engineers to track performance and adjust engine maps in real time. It's like a giant invisible nervous system. Now, this real-time track data is absolutely vital because FIA regulations severely limit physical testing just to control costs. Teams run into what's known as the Reynolds number paradox. Because wind tunnels are limited to 60% scale models and lower wind speeds, they just cannot perfectly simulate the fluid dynamics of a full-size car traveling at 300 kilometers per hour. So teams have to rely heavily on this telemetry data, along with advanced driver-in-the-loop simulators and massive computational fluid dynamic simulations, just to bridge the gap between virtual design and physical reality. Which brings us to a really fascinating philosophy for 2026. As the data shows, the fastest lap is no longer just about driving hard and deep into a corner with the cleanest braking. No, ultimate speed is now a highly calculated, data-driven compromise between aerodynamic drag, tire chemistry degradation, and preserving those megajoules of battery energy for the optimal tactical deployment. So, as we enter this new hybrid era where software maps, active aerodynamics, and automated electrical deployment strictly dictate the pace, it leaves us with one fascinating question to ponder. When a machine is half thermal and half electric, driving on the absolute ragged edge of physics, who really wins the race? Is it the driver's pure instinct or the engineer's algorithm? Think about that the next time you see them line up on the grid. Thanks for learning with me today on this Explainer.